Hello everyone, my name is Evgeny Grigoriev. I'm technical leader of RxO project. In this presentation I'm going to demonstrate common principles of RxO system, which unites core possibilities of both relational and object-oriented systems. This subject has a big history during last quarter of century, starting from the time of database manifestos. Every specialist knows about object-relational DBMS like Oracle and PostgreSQL. RxO system goes in the same direction, but it implements new and very simple logical approach to how object-oriented and relational concepts can exist together and work together on server side. This approach is evolutionary. It can give new functionality to existing relational DBMS, so customers and developers who use them can extend existing systems, existing databases in a new way, and can create new ones. In the presentation, firstly, I'll show how simple tutorial model of some enterprise is created, used, and extended during its life. We'll see a couple of new commands and also known commands modified to work with classes and objects, and we'll discuss ideas which are expressed by the commands. At the end of the presentation, I'll briefly review main internal details of RxO system. We'll see a prototype system, which implements an early variant of common syntax. The syntax has been changed considerably. It's still in progress, and the main topic of the presentation is demonstration of core RxO principles. So, later, the abbreviation RxO doesn't mean the prototype itself. It means a class of systems which implement these principles. Let's start our work. Here, you can see a window in which we interact with a simple implementation of RxO system. The system acts as DBMS, and we use text commands to manage it in the same way like SQL is used. After execution, we can see a result message. These commands after transformation are executed by SQL Server, which is a target machine, used both to store data and to perform all operations on the data. In the prototype system, Microsoft SQL Server is used as such target machine. First of all, a database has to be created in which we will work. Then, in the database, we create 4 classes. A new command, create class, is used 4 times to do it. These 4 classes form our object data scheme. Later we'll expand the data scheme by new classes using class inheritance. Classes can be simple and complex. For example, class banks is very simple. Its object has only 2 scalar fields. Class contractors is slightly more complex, because there is a reference on bank's object in the specification. In class goods, there are both simple scalar and complex tabular attributes. Here, this tabular attribute contains details on goods turnover. Also, references are defined in the structure. At last, class shipment is complex too. It contains both scalar and tabular attributes, references, and also it contains a method which performs some operations to post shipments. Constraints can be defined for classes. They are not obligatory, and classes can be defined without any constraints. A key has to be defined for tabular attribute to set its rows unique inside an object. Also, a key can be defined for class to make each of objects of the class unique by their attribute values. Foreign keys are also available. Let's create the classes. Commands create class defines an existence of a class in the system, and also it describes interface on objects of the class specification in other words. There are 2 very important points here, and these points have to be explained in details. First point is what a class is. In RxO system, each class is a stored set of objects. This feature, a class is a stored set of objects, is very important to enable a non-procedural manipulation on classes and on their data. It means that all objects of a class are accessible as elements of this class. There is no necessity to use additional concepts and mechanisms, like collection, extents, or typed tables, to build a set of the class objects. The set exists right after class is defined. To demonstrate this fact, we can execute right now a query on new defined classes. This query returns no data now because the classes haven't been implemented yet and objects have not been created. Later we will explain in details what a query is. And now we are just demonstrating that class specifications are only necessary to access data. Second point is strong distinction between a specification and implementation of classes. All class specification elements, both attributes and methods, have to be implemented explicitly. To implement the element, a command alter class realize is used. The distinction between a specification and an implementation is clear for methods, but keep in mind that our RxO system is database management system, we fill this point with new possibilities which are very important to such system. We manage data on the level of class implementation. Let's implement our classes to explain this idea. Here you can see how classes banks and contractors are implemented. All the attributes are implemented as stored. It means that all values of the attributes will persist in system, like values persist in relational tables. Let's execute the command. Implementation of class goods is more complex. The reason is that all goods turnover data can be fully produced from goods shipments data. So, if we implement table attributes turnover as stored, we will get data redundancy. A scalar field, quantity free, also contains redundant data because its value is total sum of all goods incomes and outgoes. To implement such redundant attributes, we can use queries, aggregate queries, and procedures. In this way, their values are calculated from other values existing in system. So, all data dependencies between an object and other part of system can be encapsulated inside the object to avoid data redundancy. Let's implement the class and pass to class shipments. All the attributes of the class are implemented as stored. Also, a method posted is implemented to describe actions which must be executed in the system when shipment is posted. In our test case, we change the object attributes according to simple algorithm using given parameter. Later, when we extend our data scheme, the attributes and the method of the class shipment will be re-implemented, redefined in child class. As you can see, classes encapsulate common properties of tables, views, and stored functionalities. Let's execute the command. Now, when our classes have been implemented fully, we can fill our scheme with data. We can create objects. To do it, we use new expression. Main feature of how this expression is used in our system is that this expression can be used as a non-procedural command. You know that class is a stored set of objects, and all objects are accessible as a class elements. So, there is no necessity to store references to the objects. Each created objects are accessible inside the system as a class element. Here you can see examples of these actions. In first command, we create an object of the class banks. In next command, we create an object of class contractors, and inside this command, we initialize a reference field with a reference of banks object, which was created in previous command. Here, this object is accessed as an element of class by value of the object attribute. In the third command, we create other object of class constructors and set reference field with reference on new bank objects created by nested new expression. So, new expression can be also used in usual way and returns reference on a created object. To check that the objects have been really created, we can use query to class constructors and to referenced class banks. Let's execute this query, and you can see data from the new objects. In the same way, we create two new objects of class goods. At last, we create new objects of class shipments. And here we also fill them with data of shipped goods. Quantities are positive, so we consider these shipments as goods income. Let me know that in your version of language other syntax is used to operate this object. We will see examples of commands of new syntax later. Again, we can check the data by means of queries. And as a result, we can see information about the two shipments. And now, when objects have been created, it's time for us to get acquainted with queries. It's a very important point because objects meet relations here. Complex data, which were described in object-oriented way, are transformed into relation representation. First of all, we should understand what complex data we are speaking about. Here you can see structure given in class goods specification. There are scalar attributes and tabular attribute in the structure. In the tabular attribute there is reference on constructors object, which also has an attribute referencing on banks object. Looking on the total structure from left to right side, we see a tree. A root of the tree is denoted by name of class, and leaves of the tree are denoted by names of scalar fields. Also, there are internal nodes in the tree. Let's mark out any path from root name to name of internal node. And for this path, any post paths which end with names of scalar field can be found and listed. Both this path and list of post paths are definition of table structure. In this table structure, data are represented as if the data were previously split into different tables during normalization and then were joined together on equity of key attributes. The RxO system performs all the operations to generate this table representation. Object data is represented in table form, that's why we name these tables as object views. Once again, we can take any existing tree. In this tree, we can mark out any valid path and for this path find any valid post paths. As a result, we will get definition of an object view where data are represented in a relational form. We can find many other object views started with the same path and build in the same tree many other paths to build many other object views. At last, many object views can be built in many other trees. Once again, data are represented in the object views in the way as if the data were previously split into different tables during normalization and then were joined together and on equity of key attributes. Strongly speaking, the object views are relations, and here I have to accent two important points. First of all the activities performed by our system are based on properties of relations and operations on the relations given by a relational data model. Particularly, the fact is used that relations and their attributes can have any names. So, from formal point of view, these complex expressions are just unique names. It's very important that these complex expressions carry a meaning of complex structure for data already presented in table form. They allow us to keep in mind the complex structure when we are working with relations. Secondly, in RxO system, a set of classes are represented in a set of object views, in a set of relations, and all the object views are equal relative to classes. Each classes can be represented in many different object views, and each object view can represent data from many different classes. It's possible to say that an object-oriented data description is orthogonal to a relational representation of the data. Classes and relations are two orthogonal projections on the same data pool, and these projections are united by common names used to denote both class structures and relation structures. In this way, all object data are represented in form of object views, in form of relations, and that's why RxO system is a relational system. The main difference between RxO system and traditional relational systems is how the relations are introduced, how their existence is defined in the system. In traditional relational DBMS, existence of relations defined evidently one by one, when tables and views are created by user manifestly. On the contrary, RxO system implicitly defines existence of a multitude of relations at once, when classes are created. It's clear that data from object views and from traditional table structures can be used together in queries, in join, union, and other operations. Also, classes can be used as domains for the evident tables. We already did it for table attributes. And also, mutual constraints can be set between the classes and the tables. In this way, our system can logically extend traditional relational DBMS. Let's return to object views to show all possibilities of where they can be found and how they can be used. Object views can represent data from objects selected according to some conditions. To do it, an object selection expression is used, which applied to class name or to reference existing in the tree. Object selection expressions can be simple, or they can be nested and combined to express complex conditions, which is possible in the hierarchy. In local context, we can use a tree which starts with name of a reference variable defined in the local context. Object views built in this tree will represent data about referenced object, and we keep in mind an implicit self-referencing this variable to access attributes of object which set the context. At last, any path consisting of class name or ending with reference name can be used to denote a set of objects in group operations on the objects. In all syntax which is used in prototype, such paths appear in all commands manipulating with objects. And here you can also see the new common syntax, where object group expressions are used in a very evident way. These commands consist of two parts. For clause is used in first part to determine objects, for which operations given in second part must be executed. Object views with object selection expressions, object group expressions are easy, flexible and powerful way to access the objects. We already used them when we implemented classes in our data scheme. With them, we can get data from system using ad hoc queries, change its state, execute method for group of objects, etc. Let's return to our test system to the result of the query. Later we will use this query again and again to show how it can represent data from polymorphic inherited classes. But now let's develop our test model. Note that we will extend live active model where objects already exist. We are going to create a couple of new classes and show their objects. Imagine that a necessity has appeared to sell goods and to record financial information. According to the new needs, we create class value operations. This class is very simple. There are only 4 scalar fields which contains operation ID, date of operations, expected value and posted value. Let's create this class. And now we can create other class sales, which will describe sale operations. A sale operation is a good operation on other hand, and a financial operation on other hand. That's why the class sales inherits both shipments and value operations classes. There is only one tabular attribute in this class. This attribute contains information about items of sold goods. a goods ID, a price, and a quantity. According to condition given in the table key, each goods can be sold with different prices. Now these classes need to be implemented. We will not implement the class value operations, so it will be abstract class. But its attributes are implemented in child class sales. Attribute posted value is implemented as stored, and other three attributes are implemented as calculated. A financial operation ID will be equal to a shipment ID, a value operation date will be a shipment posting date, an expected value will be calculated from pieces and prices of sold goods with the group query. Also, we define inherited method post_it. The new implementation will write posted value into stored field inherited from value operation class, add text comment special for sales objects, and fill posting date. At last, it's clear for sales operations that all sold goods have to be shipped. In fact, sold and shipped are just different titles for the same goods. The inherited tabular attribute items and the own tabular attribute sales items represent the same data with different details. So, it's a bad idea to implement both these attributes as stored, because of data redundancy. Therefore, only the own tabular attribute sale items will be represented as stored. But inherited tabular attribute items, which was implemented as stored in parent class, will be re-implemented as calculated with grouping query from the stored attribute sale items. Run all the implementation commands. Now we can create new objects which describe sales, and we can fill them with data of sold goods. Here, a second cell contains two rows where the same goods are sold with different prices. So total quantity of sold goods is 30 pieces. Let's explore our system now. Run our old query on class shipments again, and this old query returns data both from old shipments object and from new objects on child sales class. All the represented data are calculated according to different implementations. In these rows, we see values of items, attributes, which are stored according to implementation given in class shipments. And in these rows, the values are calculated, as this is implemented in class sales. Run a query on class value operations data. This class is abstract, but it was implemented fully in child class sales. So data of these child class objects appears in the result according to the class implementation. We can see ID of sales operations, which appears here as ID of financial operations. And we can see expected values calculated from sold pieces and prices. Run a query on class goods data. Here we can see 3 pieces on stock, which is calculated from polymorph tabular attribute items. According to the calculation algorithm, which considers non-posted negative pieces and reserved ones, we see negative quantities as free. Some warehouse workers can be really shocked by this fact, but it can be easily fixed in RO system, because we can change the implementation of existing objects. Let's add a special condition on negative quantity in implementation procedure. Execute the alter command. Run the query again. And the old query will return correct 0 values. So, all the data presented in object views in table form fully depend on polymorphic classes implementation, which are found and bound by system when the object view is generated. The implementations can be changed for existing classes at any moment. Now let's execute a method. We use exec command to execute a method. Here, the method is executed for a group of objects satisfied to given condition. It takes as parameter. Let's run the command and explore our system after changes. Run our old query on class shipment once again. And here we can see how the data were changed. Proper implementation of the method were executed for shipments objects and for sales objects. Posting date was also set for all the objects. Run the query on class value operations data. We can see that some value operations were posted too, and result value was calculated and written into stored fields. As you can see, the method posted re-implemented in child class sales unites the parent class's data inside the operations and affects many parent classes in Concord. Run the query on class goods data again. And here we can see correct free pieces after all incomes and some outgoes were posted. It's possible to change the method for existing objects. This is current implementation of the method in class sales. Let's change it by adding a new text command. Execute the alter command. Execute this method again for all not posted objects. Let's run our old query once again. And here you can see that all sales were posted with the new commands. And in this way we can build, change, improve, extend our object model in a very object-oriented way using non-procedural commands. And all these actions are immediately and transparently reflected into relation data representation. The class specifications themselves can be changed too. We manage the RO system as if it's object-oriented system, and we see the data in the system as if it's a relational system. According to totality of its properties, the RO system can be used in traditional two-tier client-server architecture, as the only server full of both object-oriented and relational facilities. RO server acts as an independent object-oriented tool for creation an object model of the object domain. Also, RO server is an independent environment where objects of this model exist actively. We can change the model and manage its objects. At last, RO server acts as source of relational data about the object model state. At that, RO system is an evolution both to vendors who product relational DBMS and to developers who use the DBMS. We have said already why RO system is logical extension of existing relational DBMS, but it also extends the relational DBMS technologically. RO system is just a sophisticated way to manage relational DBMS, like existing object-oriented compilers are a sophisticated way to program computers. Let's investigate some technical details on how clients interact with the server and how the server works inside. All the new possibilities can be achieved by translation of the object-oriented command into traditional activities on tables, on views, on stored procedures, etc., performed by mechanisms already exist in relational DBMS. Only parser and execution plan builder have to be changed to get the new possibilities. We can keep using existing access protocols and interfaces. We stay unchanged multi-user access control mechanism and a lot of core functionalities which maintain data, keep data integrity, perform all the internal actions and form the results. So, our approach offers an evolution for vendors because the new possibilities can be added into new versions of existing relational DBMS without their radical changes. Also, it offers an evolution for users who can continue to use existing customer systems, existing databases without any changes, and who can try new possibilities to develop existing system in a new way and to build new ones. At last, there are two reasons of why we suppose that our system can appreciably increase general performance of complex customers' information system. First reason is very simple. Our system is the only place where data are both stored and processed. There is no data shuttling at all between a database layer and other layers used to process data. A data exchange is required only to present object data on client side. Also, some negative effects like deadlocks can be avoided. Second reason concerns operations on a group of objects. Imagine that an object method has to be executed for a group of the objects. In traditional object-oriented systems, all such operations are executed by means of iterators, when the operations is executed separately for each object of the group. So, if it's necessary to execute a method for 1000 objects, the method will be executed in target machine 1000 times for each object separately. Our system acts in different way in such cases. It considers a relational DBMS as target machine and uses an ability of relational systems to manipulate total tables of some parts of the tables as a total. Our system translates a method defined for single object into such target procedure that the single execution of the target procedure in target relational DB has the same result as if the source method was executed for each object for any group of the objects. So, if it's necessary to execute a method for 1000 objects, in our system the all 1000 will be changed at once. If a query is executed which returns values of calculated attribute from all objects of some class, all the values will be calculated inside the system at once. Any operations, any algorithms, any implementation applied to an object are translated into a functionality which manipulates with data of any groups of objects at once, without any iterators, circles, cursors. This ability follows from a formality of relational data model, from common properties of relations and operations of the relations. So, our system is a sophisticated way to manage data in relational DBMS, and it uses mechanisms which already exist in DBMS to manage these data in proper way. Thus, in general, our system has the next properties. It makes complex customer systems simpler and more effective. It implements new, powerful and complete approach which fully unites possibilities of object-oriented and relational systems. It materializes new kind of server system which can be denoted as server of independent object models. It is evolutional for vendors and for users. That's why we think that our system may be interesting for many developers and end users. If you are interested in our approach in our system, if you have any suggestions, if you can collaborate or invest our project, be free to contact us. You can see our contact info on the screen and ask vendors about the new possibilities. It's end of the presentation. Our project team wishes you all the best and hope all your dreams come true.